Another way that we can communicate the magnitude and direction of a vector is by describing a vector using component form, by using its components. What is the horizontal and vertical movement of the vector to get from its initial position to its head? And so to do that, we use unit vectors that are aligned with the positive x and positive y axes, and we call them the I and j unit vectors. And they're called unit vectors because they have a length of 1 unit. So here we see I along the positive x-axis goes 1 unit in that direction, and then we have the vector j goes 1 unit in the vertical direction. So if we take a look at the example that we have below, we have kind of the information that we were finding in the previous couple of examples given to us. So we know the magnitude of the vector is 12. So we know that this length here is 12. We see the direction of the vector is 150 degrees. So we're measuring that from the positive x-axis, rotating counterclockwise. But now we want to describe this vector in terms of the horizontal and vertical movement to get there. And that is a much more functional format for us, especially when you start to perform operations with multiple vectors. So we're just basically working backwards. So I need to find what the legs of this triangle are, having been given the hypotenuse and knowing that this angle here is 30 degrees. And so if we recognize this as being a 30, 60, 90 triangle, then we can take advantage of that. If it wasn't, if it was a triangle with that wasn't one of our special right triangles, then we would have to use our calculator a little bit more extensively. But hopefully we remember that the side opposite of the 30-degree angle is going to be half of the hypotenuse. So this is going to be 6. And then the long leg of the 30, 60, 90 right triangle is root 3 times the short leg. So that's going to be 6 root 3. And if we stick with our 3 decimal place rule we can that we used earlier, we can call that 10.4. Now, the catch here is we need to indicate that as being negative since we're traveling in the left-hand direction, whereas the 6, because we're going up, is positive. So these are the two components, negative 10.4 and 6. And so if I'm going to write this vector in component form, there's a number of ways that I can represent that. One is to write it as 6, let's try that with the x-coordinate first, or x-component first, so negative 10.4i and then plus 6j. So this representation here, communicating this horizontal movement of negative 10.4 and the vertical movement of 6, has embedded in it the 150-degree angle and the magnitude of 12. So it's just an alternate representation. We could also, sometimes we'll see it written in an ordered pair format. Whoops, got a little lag there. So negative 10.4 comma 6 inside of, if we stay with our 3 decimal place rule, 3 sig figs. So we can write it in this kind of bracket format here as well. So as I alluded to, we can add and subtract vectors, perform other operations, and that component form is very useful for that. But we should take a look at just a visual image as to what adding vectors or subtracting vectors really means. So in the first piece here, where we're going to add these two vectors together, in order to add them, show what they add to in a diagram sense, we've got to place the two vectors tip to tail. So I need to translate, if I want to add a plus b, I need to translate the vector b so that it is tip to tail with a, meaning that the tip of a is at the tail of b. So I need to translate this vector. So I'm going to go ahead and take it, I've traced it, and then I'm going to translate it up so that it is now tip to tail with my vector a. So then I can go ahead and draw a vector that starts at the beginning of the first vector a and goes directly to the head of the second vector b. So here's our vector b. So together that is our new vector a plus b. So we can think of this as being the direct line that we could take instead of taking those two separate pathways. And hopefully it's evident that we could have reversed the order there. So instead of translating B so that it was tip to tail with A, I could take our vector A and place it so that it is tip to tail with B, and hopefully that diagram shows you that our vector addition is commutative. So it did not matter whether I did A plus B or if I did B plus A, I'm going to get the same vector as a result. For the subtraction of two vectors, instead of thinking of it as A minus B, for example, we can go ahead and change it to A plus negative B. And so then we can use our addition approach that we just used in the previous example. So if I want to find A plus negative B, well, negative B is the exact same magnitude of the original vector B. It's just oriented in the opposite direction, 180-degree flip. So what I'm going to do is I'm going to flip that vector around. So this green one now is negative B. And so then, if I'm adding negative B plus A, that's the same as adding A plus negative B, since we've already established that vector addition is commutative. And so then we can go from this starting point of B to the ending point of A, so from the tail of B to the tip of A, and so that's going to be our A minus B. Now, if I kind of try to recreate that diagram there, so here's our vector A, here's our vector B from our original picture. So now, if we turn it around, let's say we wanted to find B minus A. Well, that would be the same as doing B plus negative A. And so then that means I'm going to reverse A. So I'm going to turn that one around. So here now I have negative A. And so now if I add negative A plus B, we can see that we get a similar vector to the one that we got just a moment ago. But now it is oriented in the exact opposite direction. And so what that tells us is what we probably expected, is that vector subtraction is not commutative. So just like when you're subtracting regular numbers, if I subtract 5 minus 2, I get the exact opposite answer of 2 minus 5. So the same thing is true for vectors. So you get the same magnitude when you flip the order in which you're subtracting them, but your direction is going to be 180 degrees opposite. So what does adding and subtracting two vectors numerically look like rather than just kind of pictorially? Well, that's where we have to have the vectors in component form, because what we're going to do is we're going to either add or subtract the components of the two vectors to get the components of the new vector. And if we think about the diagrams that we just sketched for ourselves, that's exactly what we've done. Is we're combining the x components of each of the two vectors, we're combining the y components of each of the two vectors to end up with the components of this resultant vector. So in this case, we're being asked to find the magnitude and the direction of A and B. So we're first going to take our two vectors. So I'm going to say I want to find this resultant vector A, or R, by adding together A plus B. And so what I'm going to do is I'm going to take those two vectors that are given to me here. So I've got 6i minus 2j plus negative 3i plus 3j. And so now I just kind of have a gathering of like terms question here, where I'm going to gather up my I components, I'm going to gather up my j components to find the components of the resultant vector. So 6 plus negative 3 gives me 3i, and then negative 2 plus 3 gives me plus 1j. And so now I have the components of my resultant vector. But we were asked for the magnitude and the direction, so I'm just going to sketch this. So I'm here in the first quadrant, I'm going over 3, I'm going up 1, so here's my vector r. So we want to find the magnitude and the direction of that. So we're going to use the exact same technique that we used earlier. We're going to use a little Pythagorean theorem to find the magnitude of r. So we're going to have the square root of 3 squared plus 1 squared. So we're looking at the square root of 10. And so if we push buttons on our calculator, we're going to get 3.16 if we continue to round to 3 sig figs. And for our angle, it's going to be the one that's measuring from the positive x-axis, rotating counterclockwise. So we're going to use a little inverse tangent again of 1/3 to equal our direction. And so again, going to our calculator, we're going to find that that angle's measurement is 18.4 degrees. So again, these two pieces of information, the magnitude and the direction, is embedded in this 3i plus 1j. So it's just two different ways of communicating that same information.